Hearty welcome to all knowledge seekers to my channel. This is Dr. Madhusudan Rao Kadapa. In some other videos, I have given the detailed explanation of Kendall's notation and the birth and death process using which we can derive the expressions for different queuing models based on birth and death process. Now in this particular video, I am going to explain a typical problem in single server queuing model. Now let us have a look at the problem. Here a milk plant which distributes its products by trucks. So the trucks are loaded in the dock. The company has its own fleet, but it is not sufficient, so it also operates some trucks of private transportation company, and that private transport company will provide 40% of the total trucks. The transport company once complained that its trucks have to wait in line and thus it is losing money paid for the truck drivers for their unproductive time, that is the waiting time of the truck drivers. So the trucks arrive all together, that means the company trucks as well as the transportation providers trucks according to Poisson process at an average rate of 3 per hour, and the average service rate is 4 per hour. So this is the problem. Here we have a milk products company which has a single dock, and here we have to find out using the given information the probability that a truck has to wait, the average waiting time for a truck, expected waiting time of company trucks per day, cost of waiting time per day for company trucks at the rate rupees 150 per hour, assuming that the cost of idle time of server is insignificant. See, in queuing systems what happens, if server is busy then customers have to wait, so their waiting time cost has to be considered. In the same way, if there are no customers, the server will become idle and his idle time cost also has to be considered. But here in this particular problem, the idle time cost of the server is insignificant, because in companies where there is loading and unloading, then naturally what happens, once a truck is loaded, the loading people, the hamalis or whoever we call, they will be making uh, crates or the cartons, whatever it is used to transport the products. They will make it ready for the next truck. So absolutely the servers may not be idle even in between departing one truck and the next. So now we have to calculate these four things. Here we have the mean arrival rate of trucks is 3 per hour. On an average 3 trucks arrive per hour and the mean service rate is 4 per hour. Then utilization factor is the ratio of mean arrival rate to mean service rate. So it is 3 by 4, which is 0.75, which means 0.75 is 75% of the time the server is busy. So for the remaining 25% of the time, the server may be assumed to be idle, but he may be occupied with some other task. Now first thing we have to determine is the probability that a truck has to wait is 0.75, because 75% of the time the server is busy. Then average waiting time for a truck is Ws, which is 1 by mu minus lambda, which is equal to 1 by 4 minus 3, which is 1 hour. So this time includes the waiting time in queue as well as the service time. And coming to the expected waiting time for company trucks per day. So here, whatever the time they spend, why we have calculated WS there, means the total time spent by the customer, maybe a truck or truck driver, that means including truck driver, which is 1 hour, which includes the service time also, that means the loading time also. But here the complaint is that the waiting time of the trucks, the transportation providers trucks, that cost is important. So as the mean arrival rate is 3, now we have to find out the expected waiting time for company trucks per day in queue. Here it is 3 into 8, because assuming 8 hours day, so totally 24 trucks will arrive in a day, multiplied by 0.4, that is the percentage of company trucks. So as we have seen in the problem in the beginning, 40% of the trucks are provided by the transportation company, multiplied by WQ, waiting time of the customer, in the sense the truck driver in the queue. So it is lambda by mu into mu minus lambda. So 24 into 0.4 into 3 by 4 into 4 minus 3. So 4 6 are 24. So 6 into 0.4, it is 2.4. 2.4 into 3 in the numerator, which is 7.2 hours per day. And the cost of waiting time for company trucks per day is 7.2 hours multiplied by hourly rupees 150, which gives rupees 1080. This is the cost of waiting time for company trucks per day. So with that, our problem is over actually. Now we can extend this problem. Suppose at present the company, milk products company, utilizes 2 persons to load the trucks, and what if the company wants to check what if the service rate can be increased to 6 by deploying one more worker. See, with 2 workers it is 4 trucks per hour. Adding one more worker, we can make it 6, and the wage rate per worker per day is rupees 600. Check whether the decision is worthwhile or not, because the truck company, that is the transportation provider, is complaining that the waiting time of his drivers is wasted. Now let us check adding one more worker for loading will decrease the waiting time cost for the company trucks. Now with the existing service rate, where the company were employing 2 workers for loading, the total cost is wages of 2 workers per day plus cost of waiting time for company trucks per day. So it is 2 into 600, because the wage rate is 600 rupees per day per worker, plus 1080 was the cost we have calculated for the waiting time for company trucks in queue. So put together it is 2280. Now let us consider what if we use 3 workers in place of 2 workers, and how it will change the waiting time in queue for the company trucks as well as the effect on total cost. So by deploying 3 workers for loading trucks with enhanced service rate, as usual the mean arrival rate of trucks is 3 per hour, and the mean service rate now it is 6 per hour. Now the expected waiting time for company trucks per day is number of trucks per day, which is 3 into 8. For 8 hours day it is 24, multiplied by percentage of company trucks, which is 40%, which is 0.4 as usual. But here WQ will change, because here mu is 6, so it is lambda by mu into mu minus lambda. On substitution we get here it is 3 by 6 into 6 minus 3, so 6 4s are 24. Here 6 minus 3, 3 gets cancelled, so 4 into 0.4, it is 1.6 hours per day. Now the total cost for the proposed system with 3 workers is the wages of 3 workers per day plus cost of waiting time. So here the wages for 3 workers is 3 into 600, which is 1800, plus the waiting time cost for the company trucks is 1.6 hours multiplied by 150 per hour, which is equal to 240 rupees. So put together it is 2040. Earlier it was 2200 something, but here it is 2040. So there is a saving in the total cost. Hence, with 3 workers, the total cost is minimum, and it also minimizes the waiting time cost for the transportation provider. But there is some little additional cost to the company, but there is overall saving. So it is worthwhile to deploy one more worker to increase the service level. So that is how we can solve this kind of problems. Thank you very much. In some other video I will explain some other interesting problems in single server queuing model. Thank you.